Hello, welcome back to the PhysioDesigner tutorial series. In this tutorial, we will create a serially coupled Bonhoeffer-van der Pol model, called BVP model, which shows the excitation wave propagation. We have already seen the single BVP model in the previous tutorial. Actually, we derive the model starting from a damping oscillator. The BVP model with these parameter values on the slide shows excitatory dynamics for the external stimulus. Now we consider to create a coupled model by connecting some of BVP models with gap junctions serially. A gap junction calculates the difference of the membrane potentials of adjacent two BVPs, and by multiplying it by a conductance, it provides a current flowing between those two. Only the first BVP model receives an external stimulus. Before starting, we introduce the template instance framework of PhysioDesigner, which helps the process to create rather large-scale models, or models including repeated structures, such as multiple BVP models appearing in this example model. There are two ways to create such repeated structure. One way is to copy a module and multiply it by pasting it several times, and the other way is to define a template module at first and create instances of the template module. In the former way, all modules created by copy and paste are identical to each other and independent. Hence, when you want to change some parameter values of those modules, you need to do for every module one after the other. In the other words, you can change each of them independently. There is no guarantee to be identical after some modifications. In the latter way, all instances are identical to the template. Hence, if you change the parameter values at the template module, the changes are immediately valid for all instances. Besides that, it is allowed to change only the static parameters values and initial values to give numerical characteristics to instances. But the other properties defining the dynamics cannot be modified on instances to ensure the sameness between the template and the instances. To begin modeling, let's load a BVP model in the sample directory bundled in the PhysioDesigner package. The file name is BVP Pulse PHZ. We set the BVP module as a template. Before that, we cut the functional edge from the pulse generator module to the BVP module to separate those modules. To make the module a template, right-click on the BVP capsule module and select Template in the menu. Then a label of template appears on the capsule module, and also all modules inside. Notice that to make a template, modules must be encapsulated. Okay, now we have a template of BVP model. Next, we will create a gap junction template. Create a functional module, in which we will define several physical quantities. In the gap junction, the difference between two membrane potentials is calculated. We need to prepare two variable parameter type physical quantities to receive those values from BVP modules at outside. Firstly, let's create V1. Its type is variable parameter. At the Implementation tab, select Assign at the definition type. There is no import now. We need to create a new port, so input its name in the text box and click Add button. Here the name is V1, but can be any. Similarly, let's create V2. It also needs to create an import for V2. Next, let's define the current flows through the gap junction. It is defined by the difference of two membrane potentials multiplied by the conductance. Here the conductance G is used, but not defined yet. So the system asks you if you want to create a physical quantity automatically. Click OK button. The new entry for G is created as a static parameter type, and this is OK now. You don't need to change it. Set the value 1.5 for G at the Implementation tab. Then we need to create the second current I1, which is defined as -I2. Why do we need to prepare two currents? This is a little bit tricky, but reasonable enough. Let's consider that the current flows from the second BVP module to the first BVP module in the serially coupled model. The current inputs to the first BVP. In the other words, the current flows out from the second BVP. These currents have to be represented in the equations of both BVPs, which are the same value, but with the opposite sign. Hence I1 is equal to minus I2, and in this case, I1 is imputed to the first BVP, and the I2 to the second BVP. Alright, we completed the gap junction. Let's close the physical quantity dialog by clicking OK button. We still need to create two outports to output the currents I1 and I2. Right-click the module, and select Edit Ports. In the dialog, lower table is for outports. Double-click a cell at the name column, and put I1. Then select I1 in the combo box at the physical quantity column, similarly for I2, and close the dialog. Finally, let's encapsulate the module. Select Encapsulate in the context menu. Then create two imports and two outports on the capsule module. Open the port dialog again, and create them. In this case, because there are no physical quantities in the capsule module, you don't need to select physical quantities at the combo box when creating outports. After closing the dialog, let's link ports on the capsule module to those on the gap junction module. By these links, for example, the values arrived to the import of the capsule module can be forwarded to the gap junction module's imports, and the values output from the gap junction can go out from the capsule module. Finally, set it as a template. Now we have all parts to create the serially coupled BVP models. Just in case, let's save the model into a file. Then next, let's create instance modules to compose serially coupled BVPs. Select Make Instance Modules on the context menu, appearing clicking the right button on a template. In the small dialog, input the number of instances that you want to create. Here we will create 8 instances of the BVP template. Then the instances appear on the canvas. They are shown as a bundled one module. Similarly, create 7 instances of the gap junction template. To expand the bundled instances, click right button on it, and select Expand. Instance models are displayed separately. Notice that every instance is labeled by number. From now, we will link instances of the BVP and of the gap junction by functional edges. To make the process easier, before linking them, let's relay out those instances. Select Tool, with an arrow icon at the toolbar, to enable to select multiple modules at once. Now, because we are going to create a model composed of modules connected serially, let's align them in line. To put a little bit more space equally, move the rightmost module to the right a little bit. Then select Instances, and select a command in the menu, Item, Distribute Modules, Horizontal. Also to align them straight, select Align Modules, Horizontal, in the menu. Similarly, let's align instances of the gap junction, and move the instances of the gap junction upward. Now, let's link instance modules. One gap junction module receives inputs, which are membrane potentials, from adjacent to BVP module, and it sends one output, which is a current flowing through the gap junction, to both of BVPs, respectively. This part is a bit boring. Let's fast forward the movie a little bit. Finally, we will link the external stimulus module to the first module in the series of BVP instance modules. Let's modify the stimulus a little bit. Change the value of the pulse width from 40 to 20. The model is almost completed. Finally, we need to change the value of a parameter C in the BVP, and to take care of the initial values of the instances of the BVP. The parameter C should be 3 in this model. This parameter is involved in both of excitation and refractoriness modules. Regarding the initial values, Since instance modules inherit all properties from the template by default, the initial values are also the same. Hence, when simulations are performed, all instances start from the same point. To avoid this situation, we will modify the BVP template and use Uniformvariate function to generate random values in the definition of the initial values. The first two arguments of the function, -1 and 1, mean that it generates a random value between -1 and 1. In a simulation, random values are generated in individual instances independently. We need to modify the initial values in both of excitation and refractoriness modules. Congratulations! The serially coupled BVP model is finally completed. Let's save the model. Now, let's run a simulation. Call Flint from Simulation menu. To reduce the number of dumped simulation point, set 10 at the data sampling. This model is still small, and the simulation finishes quickly. Go Details and View. To observe the simulation result, we will observe the time course of variables named xi, at, number. Here, the number after at mark represents the label of each instance, and is from 1 to 8 here, and also adds stimulus current. You see that there are 8 excitation waveforms with gradually shifted initial rise point. It shows excitation propagation through from the first BVP to the end. Now let's observe the simulation results with pH plotter, which can display a little bit different way. Save the simulation result into a file in ISD format, which is a binary format defined used in Flint. Launch pH plotter, which is downloadable at physiom.jp, and load the file. Select the file name in the leftmost list box, and tick the checkbox at left side of the variable's name to draw graphs. To zoom into one part, select Lockbox in Zoom box. It is possible to display these curves with slightly shifted baseline. In this way, the waveform of each curve can be observed separately, and you can observe the manner of the propagation more clearly. To do this, open a Preferences dialog and go to the Plot tab. Tick the checkbox at the base shift plot, and set -0.3 in the base shift text box. And set the plot range for X and Y axes at the Axis tab. Click OK button to close it. Now you see, the baseline of the every curve is slightly shifted. Each curve is separated, and shape is clearer. The onset point of the excitation is shifted little by little towards right, meaning the excitation propagates from the first BVP to the end in the line, via gap junctions. But the endpoints of the excitation are not different much, and obviously the wavelengths are shortened as the excitation propagates. If you create longer line, and give a periodic stimulus to the first BPV, you can observe more interesting features of the excitation propagation. Especially, try to observe the manner of the excitation propagation with changing the period length of the stimulus. It can be interesting. Alright, this tutorial finishes here. Thank you very much for listening. Goodbye till next time.